Swayam Prabha. Digital India. Educated India.
For complete feedback linearization, we have this new result. This result we will try to prove and understand, okay? Because it's simply based on using the Frobenius theorem, alright? And going back to our earlier conditions. The first condition was that the first requirement is that you have, notice that it's a necessary and sufficient condition first of all. Then you are saying that this matrix is full rank and this distribution is involutive, okay? Great. How do we prove this? The necessary and sufficiency. If you remember, we can go back to what we required for feedback linearization earlier, right? We required that, you have this sort of thing happening. What is this? Do you remember what this was? If you have an output y equal to lambda x, right? Then you wanted its derivative. When you take its successive derivative, you want the control to not appear, okay? Because we are talking about relative degree n. So we go all the way to n minus 2, okay. This means that control does not appear in the n minus 1 derivatives, okay, only in the last one. And then you also required that LGLF n minus 1 lambda is actually not equal to 0, right. Basically it is just saying that you take, when you take the nth derivative, the control appears, okay. This is what this is saying, right. This is how we did it. We said that you had an output function y equal to lambda x, yeah, or in that case we use hx, it does not matter, just notation. And if you keep taking derivatives of lambda, control should not appear in the first n minus 1th derivative, but should appear in the nth derivative. That was this condition, okay. Now we are going to basically say that this is going to imply complete integrability, okay. How? You remember that this set of conditions by lemma 0.1 is identical to this conditions, right. All the LGLF can become addf, yeah. I am not going to go back and show you the lemma, but because we remember this, yeah. It just becomes addf 0, addf 1, addf 2 all the way to addf n minus 2, yeah. If these are 0 all the way to addf n minus 2 g is equal to 0, okay. And similarly using this, you can show that addf n minus 1 g times lambda is not 0, okay. Pretty straightforward to show. So we already did this before, okay. Now from this, what we have already shown again in lemma 0.2 is that these are linearly independent vectors, okay. How? Okay, now I have to swipe back. I apologize. Let me go back here, and if you remember, we proved this using a kind of matrix multiplication, right? And we had two matrices, right? Just look at this, yeah. We proved the linear independence of the DH functions using this product, right? And we showed that this product is rank R. Therefore, individually each of these must be rank R, okay, which means these are linearly independent, okay, which means these are linearly independent. As is this, in this lemma of course our statement said that these are linearly independent, but we also proved that these are linearly independent, right, because if the product is rank R, then individually each of them are rank R, okay. Great. So this is what we are using. So we go back and there the R gets replaced by n, that is all. So we know that this is now a set of linearly independent vectors, okay. So this is the first thing. We already proved the first requirement. We are going backwards, that we already proved that these are linearly independent, done. Now we only are left to prove involutivity of the distribution, okay. There we are going to use the Frobenius theorem. What? How do we do that? D is a span of these guys, so obviously it's non-singular and n minus 1 dimensional. We've already said that, right? Okay. So this condition that you have, this guy, yeah, this condition can be written as this, just in matrix form. Yes, this is precisely the integrability condition, right? This is the same as this, correct? So this is exactly the integrability condition, right? On G, add of G, add of n minus 2G. Huh? Yes. So we are done. What we have shown, what have we shown? We have shown that the distribution is non-singular, and we have shown that the distribution is integrable, right? Because in this case you had, right, you have k equal to, in this case this is what, k equal to n minus 1, right? This is k equal to n minus 1, right, because you have 1, 2, n minus 1 vectors in the distribution. So k is equal to n minus 1, therefore how many h functions we are going to get? Only one, because n minus 1, n minus k, right? So only one h function, that is this lambda, okay? And this is what we had, right, in our earlier feedback linearization result also, that lambda was the output function. Here this is this lambda, alright. So now here if you notice, this lambda becomes the output function. In the partial linearization I said that it could be the output function, but it could also be the extra coordinates that we were talking about, okay. But in any case, so you have here this lambda as the output function, because we have already proven that D is non-singular and integrable, it means that D is involutive, right, and that is the second statement, okay. So one side of the proof is done, alright. Now we can also prove the other side similarly, okay. So from the two conditions we have that the distribution is non-singular and involutive. This is our assumption. Therefore by Frobenius theorem D is completely integrable, which means there exists an H such that this happens. Yeah, and what is this? This is nothing but LG, L add of G all the way to L add of n minus 2G. Yes, just by multiplying this out. Yeah, and again I go back to lemma 0.1. So you see the lemma 0.1 and 0.2 are regularly getting used. So if I go back to lemma 0.1, all these L add of 0, add of 1, add of n minus 2 is basically LG, LG, LF, LG, LF n minus 2, okay. So I got one condition that is required for feedback linearization, right. The other one is that LG, LF n minus 1 has to be non-zero, okay, alright. How do I prove that? Okay, I take DHX, which is a 1 by n vector, and I multiply it with this additional quantity here, okay. I take this whole guy, but then I multiply with this, okay. So what does the product give me? It gives me zeros in the first, all of these become zeros, right, because of this guy, but then I get this last piece, right, then I get this last piece. Now what do I know? I know that this is full rank, right, this is a full rank matrix, and this is of course not zero rank, right, this is rank 1 at least, because it is just one coordinate, right. So if I take partial and it's 0, it's not a function at all, yeah, it's a constant, it's not a coordinate anymore. So this is at least rank 1, well at least at most rank 1, because it is a row vector. So what do I have? I have the product of a rank 1 matrix and a rank n matrix, okay. This is a rank n matrix, this is a rank 1 matrix. So the product cannot be less than rank 1, right, because the rank of the product is actually the minimum of the rank of each of the entities. So the minimum is 1. So this has to be rank 1, cannot be rank 0. If this is rank 1, this is not 0, right, okay. So same tricks, if you remember, the tricks that I am using are the same. Use lemma 0.1, lemma 0.2, take products of matrices, show that the product has some rank, okay. That is how we are doing things, okay. So because the individually each of them, this is rank 1, this is rank n, so obviously the product cannot be less than rank 1, yeah. So therefore this has to be non-zero. So we've just proved that this guy is non-zero. So we are done, right? This is what is the conditions we require for feedback linearization. In fact, H again becomes the output, the desired output, okay. So, and this is what we can use to come up with the output, okay. So we did the DC motor example, right? If you, let's go back, this was the DC motor, yeah. What did we do? We verified this 0.1, 0.2 and so on, and did we try to, yeah, we also found a feedback linearization, right? We found a feedback linearization, and in order to do the feedback linearization, we actually already had an output, correct? We already had this output, which is this, yeah. In this case, at least the model that I had used, I don't know what is the model coming up, I don't know, but at least the model that I used had relative degree what? What was the relative degree in this case? 2, right? Relative degree was 2, not 3. So this was not completely linearizable, okay. So the relative degree was only 2. That is why, if you remember, I had chosen this extra state, right? I had chosen this additional state, right, which was the phi to make the diffeomorphism. All right. So let's keep this in mind. What was the dynamics? This, and this was the output, okay. So somehow my feeling is that the dynamics that we'll have now is something different, okay. All right, that's fine. Let's go and see what happens. Let's not worry. All right. So what is the DC motor dynamics that you have here? This is what I mean. There is a proper with network and electrical voltages and L and R and so on. Yeah. So we have all the nice the proper equation, the electrical dynamics on the stator side, then you have the electrical dynamics on the rotor side, then you have the mechanical dynamics of the rotor, okay. So this is the mechanical part and the other two are the electrical parts. You have inductances, the resistances, the back EMF, the rotor inertia, angular speed, friction and torque, okay. So this is the torque developed at the rotor shaft. All right, so there is, yeah, I mean I'm just going to skip to this part, okay, yeah. So this is the dynamics of the system, yeah, Fx plus Gxu, okay. Now yeah, there was an error here, there was an additional 0, this should be only 3-dimensional, right, cannot be 4-dimensional, it's because it's a 3-dimensional state space. So I just remove this. But does this match the dynamics we had for the DC motor is what I am wondering. Yeah, this was it. So because I took the dynamics from Khalil, I really don't know if so let me paste it here. Now does this look similar to this guy? X1 dot is minus x1 plus u, yeah, similar, alright. X2 dot contains some x2 term and a constant and an x1 x3, similar. X3 contains x1 x2 and an x3, this is not similar, okay. There is some additional term here, I don't know what it is from. I think in that model clearly looks like the friction term is missing, okay. In the earlier model, in this model you see the x3 dynamics has this missing, yeah. So it looks like there is some, and that x3 is coming from this guy, yeah, that's the friction model it looks to me like, or am I missing something? Yeah, x3 is omega, yeah, looks like it's missing the, I mean the model I believe that I took from Khalil is missing the friction, okay, maybe whatever, very good DC motor, alright. Anyway, so we have this model, alright. Now the question that we want to ask is, can we fully feedback linearize the system? How do we verify this? We are given two conditions, right? First is that G, you have to verify this G add of G and add of squared G, right? Why? Because the 3-dimensional system, right? And we want add of n minus 1 G until add of n minus 1 G, we want this to be full rank. Now let's do some computations, okay? What is G is this guy, okay? What is add of G? I have already written it. Add of G is this, okay? How do you compute add of G? I want you to compute. I want you to verify. How do you compute add of G? Otherwise you folks will get completely lost, okay? You are given G 1 ls 0 0 and you are given f. Well, actually I am not going to rewrite this. So add of G is what? It's the same as Lie bracket of fg. Excellent, excellent. All right. And this is what formula? First you do the second one, dgf minus dfg. Always remember, the first term is the Jacobian with respect to the second argument. Karo, I will do this in a smart way. First of all, dg, if you look at dg, what is dg? What is dg? Jacobian of this. Yes, 0. It's a constant, right? Constant things don't have derivatives, right? So this guy is gone already. Okay, no first term. All you are left with is the second term. Okay. Now you have to play it smart. I would not compute all of it. What would I do? I am doing df times g. So some matrix multiplied by g. So what do I know? The g has last two elements 0. Okay. So do I have to compute the entire matrix? What will I compute? First column, right? First column of df is enough because it will be multiplied by the first element of g. So that's all I am doing, just computing the first column. What is the first column of df? No, I mean, what is the expression? How do you compute first column of df? Okay, what is df? Expand df for me in terms of actual partial derivatives. First column is what now? Absolutely. Del f1, del x1, del f2, del x1, del f3, del x1. Right? That's the first column, right? That's how I am doing this. So all I am doing is taking partial of each of these with respect to x1. Right? So that's what I did. Look at this. Minus rs by ls. How did I get a square? I have no idea. I don't know. God help me. I don't know. Don't know how I got this square. No square. There's no square here, right? Did I miss something? Am I right? What about del f by del x1 of this guy? Just this, right? Minus k lr. What? Why am I missing everything? Acha, I have already multiplied. Oh, see, you guys don't tell me when I am right. Alright, this is correct. I have already multiplied by g, no? So obviously 1 by ls is multiplied. So rs by ls, 1 by ls, right? This is correct. Yes? Partial with respect to x1 is just minus rs over ls multiplied by 1 by ls, rs ls squared. Done. Partial with respect to x1, just this, multiplied by ls is this guy. Third term, partial with respect to x1 is this, multiplied by ls again, this. Excellent, excellent, excellent. Now, done. What about add f squared g? This is f of fg. Now it's not nice anymore because fg is now this. Yeah, Fg is now this guy. Huh? Let's see, did I do this? Apparently I did not do this. Okay, let's put some effort and do it. And what else? I have Fg. Okay. All right, folks. Now we are going to work. Now what is add f squared g? Okay, this is equal to f comma fg. Okay, this is what we have to verify. Linear independence. As of now, what have we obtained? We have obtained g, which has something in the first element. All right. Then we have obtained this guy, which has also something positive in the or whatever non-zero in the first element. But then you have some funny things happening here. I don't know. All right. But we are going to compute this. This is what d fg f minus df fg. Okay. Now what? First row. Compute dfg. Fg is written here. Take Jacobian and tell me what is the first row. Can't take so much time for first row. Huh? Thank you very much. Just be confident. I will shout at you later. All right. Okay. Second row. Correct. Correct. Got it right. Third row. Third row. I can't hear anything. Okay. All right. Then you have this f. Ooh, nice. Whatever it is f. I'm not even going to write it. I'll do the multiplication later on. df minus r over s. Sorry. R over ls. 0 0. Okay. Second. RR LR, and then third is minus KLS LR times x1. Third one. Yep. KLSJ x2. But do you prefer this or the Frobenius theorem proof? This one? At least you can write something, right? In that one it is K ls by j times x1 and f by j times what? Minus rs by ls squared minus k lr x3 k by j x2. Whew. Anything nice is coming out of here or what? Or nothing is going to be nice here, is it? That's the whole idea, right? Okay, let's just look at this guy. What is this guy? The first row is 0, so I have a 0 here. What about the second row? It is just minus k over lr multiplied by f by j x3 plus kls by j x1 x2. Wow, nice. Oh, this is just not nice. We will try to avoid such cases. Minus rr by lr x2 plus vr by lr minus kls by lr x1 x3. ठीक है, minus this whole guy. Okay, I'm not even going to try to expand this. Okay, what do we have to do? We have to now say that this is full rank. So what he is saying is that it is full rank if x2 and x2 or x3 are non-zero. Okay. All right then. Let's see. We already have G, which is giving me 1. Here, if either x3 or x2 is non-zero, this is going to give me another independent vector. All right. This one I really don't know. I mean, I don't see how this can be simplified any further. Yeah, I really don't know. I mean, I assume that this will also give me something like, unless I missed something. This is correct though. This is correct though, because I have already written it before also. Yeah, this is not turning out to be simple, but I guess if x3 and x2 are non-zero, then this should be fine too. Yeah. I really have to check, or you guys can check. I don't know. Yeah. I wouldn't usually make up an example like this, but that's fine. Yeah. In fact, what I was wondering was, in our case we did not have the friction term. So how did that impact the linearizability is what I was wondering, because all that is getting rid of is some of these f terms here, which is here and here in some very few places, to be honest. Yeah, this is, I will say, to be completed offline. Yeah, you can do it on your leisure time. Yeah, or you can even check it numerically. Yeah, just feed it and then just plot it, and if it doesn't hit zeros, you're fine. Okay, rather than actually doing the whole thing, doesn't make sense, to be honest. Okay, let's go to the second condition. What was the second condition? You want the distribution to be actually, well, we need involutivity, right? We need involutivity. Okay, we want involutivity of the in this case G and add of G. Okay, only two vectors. The add of square G is not required. Yeah, because we are looking at n minus 2, here n is 3. So we are looking at the distribution which is G and add of G, and this you want to be involutive. That should be relatively easy. But actually, what is there to prove, because we have only two. Okay, all right, sure. We have G and add of G, and what we want to claim is that G comma Fg belongs to the distribution. Okay, this is the involutivity, right? Because the distribution is just consisting of yeah, but this should be easier to find. Yeah, why? Because this is what, dg times Fg minus dFg times G. What do I know now? What is dg? 0, right? So dg is 0. So this term is 0. Okay. So, and I know that G only has element in the first, there is only the first term. So I only have to compute the first column of this guy. Okay. I believe we've already done dFg is this guy. dFg was this, right? What is the first column? 0. So obviously 0 belongs to delta. I mean, if you have any vector space, 0 is an element of the vector space, if you are confused. Yeah, or if you don't like to look at it like that, you can think of, I take G 1 times G minus 1 times G, still have 0. Okay, any vector space contains 0. Okay, so it is the 0, so trivially true. Okay, so implies delta is involutive. Okay, which means that delta is completely integrable. So what does that mean? It means that if you take some function beta and you take its gradient or whatever, you can call it d beta multiplied by the elements of the distribution, that is g and add f g, that is equal to 0, right? This is the condition, right? And so this gives again what? A partial differential equation, right? Because this grad b is what? Partially with respect to x1, x2, x3 multiplied by these, okay? Alright. So let's actually try to evaluate this. What does it give me? I mean, I don't know why he keeps changing notation. Anyway, you have d beta multiplied by terms of the distribution, which is g and I will say add fg, and this is equal to 0, yeah, by complete integrability. Alright. So we'll use this to actually compute, yeah.